Okay, so our next form of differential equation is the exact differential equation, as you can see on the first slide of this lecture. So last meeting, we discussed already two forms, the variable separable equations and the homogeneous differential equation. For today, we will be having again another two forms of differential equation, the exact differential equation and the linear differential equations. So let me start first with exact DE. So if there exists a function of x and y such that its differential df is exactly equal to the left side of the first order differential equation represented by m as a function of x and y dx plus n as a function of x and y dy is equal to 0, that is df is equal to that first order differential equation. Then m as a function of x and y dx plus n as a function of x and y dy is said to be an exact differential equation. What does it mean? What is that mentioned total differential or the differential df? So if you have here the function, if you have here this function of x and y, when we take its total differential, you actually take df, you take the partial derivative of f with respect to the variables. So that would be the partial derivative of f with respect to x dx plus the partial derivative of f with respect to y dy. It means that if this total differential, partial derivative of f with respect to x dx plus partial derivative of f with respect to y dy is exactly equal to this m as a function of xy dx plus n as a function of xy dy, which clearly means that the partial derivative of f with respect to x should be equal to m, and the partial derivative of f with respect to y should be equal to n. If that is the case, then that given differential equation is said to be exact. Okay? So since today our topic is about exact differential equation, we have to know if that DE is really an exact DE. And we need to have the so-called test for exactness. And the test for exactness is this. You have to take the partial derivative of m with respect to y and the partial derivative of n with respect to x. If the two are equal, then the given differential equation is said to be exact, provided that mn, the partial derivative of m with respect to x, and the partial derivative of n with respect, sorry, the one is with respect to y. Let me correct this one. This is with respect to y, and the partial derivative of n with respect to x are continuous functions of x and y. Okay? And then knowing that it is an exact DE, then the next thing that you have to do is to provide the solution. And this is the method of solution as presented in this slide. If you are again given of a differential equation which is found to be exact, then you have actually two options of solution. The first one is you may use m, and the second is you may use n. So for this slide, you are to use m, in which the partial derivative of f with respect to x is equal to m as a function of x and y. And we are actually to solve for the solution, the function of xy. This is what we are going to look for, the solution for that exact differential equation. So we are actually to integrate m with respect to x plus t of y. What is this t of y? Normally, when we take integration, we put the constant of integration. But since we integrated m with respect to x, it means that y is held constant. So instead of putting here plus c or constant of integration, we put plus t as a function of y, since y is held constant. So this function or this term may be a constant or it can be a function of y. And again from the previous slide, that is an exact DE if the partial derivative of f with respect to y is equal to n. So equating the two, you have here the partial derivative with respect to y of f, in which this is your f, which is the integral of m as a function of x and y dx, plus the derivative of t of y is t prime of y. So we equate it to n. And from this equation, we determine t prime of y. Because here, our target is to find your t of y to be added to the integral of m as a function of xy dx. And from that equation, t prime of y is n by transposing this first term to the right. That is n as a function of xy minus the partial derivative with respect to y of the integral of m as a function of xy dx. And we need to find t of y, therefore we integrate with respect to y. And the implicit solution of the equation is a function of xy is equal to c. That is using m. Similarly, if you are to use n, so if n, then n as a function of xy is the partial derivative of f with respect to y, since it is mentioned that if it is exact, then the total differential of f should be exactly equal to the left side of that first order ordinary differential equation. And again, we integrate with respect to x. No, this is with respect to y, sorry. Because the constant here is function of x. So with respect to y, it means that x is held constant. So this is again our constant of integration. And similarly, analogous to that of using m, you will be obtaining your t prime of x to be equal to m as a function of xy minus the derivative with respect to x of the integral of n x and y dy. And you have to integrate again with respect to x to find t of x. And the implicit solution is the same as that of the previous slide, which is the function of xy is equal to c. Maybe you don't appreciate the method of solution presented on these two slides. What those steps or procedures mean. We can have the sample problem for that, for you to be able to understand what is actually that solution. Okay? So let us have the following examples. I will be discussing with you 4 examples for exact differential equation. And to give you, let us have the first example. Solve the differential equation x plus 2y dx plus the quantity 2x plus y dy is equal to 0. Okay? So you have here, if you're going to inspect this differential equation, this equation is actually a homogeneous DE because you have x, 2y, 2x, and y. So this is homogeneous. But let me show you also the solution if we are to use and to have the solution of an exact DE if it is found to be exact. Okay? But again, some differential equations can take several forms. And whatever form it is, you provide the corresponding solution. If, say, for example, this is homogeneous, you can solve using homogeneous DE solution. If it is exact, then you can also solve using exact, but you have to obtain the same solution of this differential equation. So let us have first the test for exactness. So again, this is your m dx, and this is your n dy. Test for exactness, we obtain first the partial derivative of m with respect to y. Taking it with respect to y, it means that x is held constant. So the partial derivative of m with respect to y is 2. And the partial derivative of n with respect to x is also equal to 2. Since they are equal, then it means that the differential equation given is exact. And what would be the procedure? So that is actually step number 1. Determining whether the given DE is exact or not. Number 2 is you solve for the solution already, which is a function of x and y. Again, in this step, you may choose whether you use m or you use n. So to illustrate first, let me use m is equal to x plus 2y. So you have to integrate with respect to x. So f is equal to the integral of x plus 2y dx. And integrating with respect to x, it means that y is held constant. So you have here x squared over 2 plus 2xy plus the constant of integration. Again, since it is with respect to x, we will be having y as constant. Therefore, we have t as a function of y. And then, after that, the third step is you have to differentiate with respect to y to find your t prime of y. So the partial derivative of f with respect to y is equal to what? So x now is held constant. Okay? So here, derivative of this is 0, and the derivative of here is 2x plus t prime of y. But since the differential equation is found to be exact, and we say that when it is exact, but the partial derivative of f with respect to y is equal to n. So therefore, equating the two, you have here your 2x plus t prime of y is equal to n. This is our n, 2x plus y. So you have here 2x minus 2x, and therefore your t prime of y is equal to y. And then, the fourth step, since we are to find t of y, then you integrate with respect to y. So the integral of t prime of y is equal to the integral of y dy. So t of y, therefore, is equal to y squared over 2 plus c. And then after that, you substitute this t of y to this. Therefore, your function of x and y is equal to x squared over 2 plus 2xy plus y squared over 2 plus c is equal to c is equal to c. Do not put it 0 because we do not know what is this c and the constant of integration on the right. So simplifying by multiplying both sides by 2, then you have x squared plus 4xy plus y squared is equal to c. And that is the solution of that exact differential equation using m in the solution. Okay? Now, let us try an alternative one. So, we are done with the first method or the first step. So, punta tayo dun sa second one. We use this time using n. So, if we use n, we integrate with respect to y. So, kabaligtaran nung variable natin ditong ginamit sa m. So, f therefore is equal to the integral of n, which is 2x plus y dy. So, f here is equal to, so x is held constant. So, you have 2xy plus y squared over 2 plus the constant of integration, since with respect to y, you have here t of x, which is the constant of integration. Then the next step, number 3, is we differentiate with respect to x. So the partial derivative of f with respect to x is equal to, so y is held constant. So this is, tama ba? 2y. So y is held constant plus t prime of x. And again, since it is found to be exact, but the partial derivative of f with respect to x, since we use n, is equal to m. So equating the two, you have 2y plus t prime of x is equal to our m, which is x plus 2y. So 2y and 2y, therefore t prime of x is equal to x. And the fourth step is we integrate with respect to x. So the integral of t prime of x is equal to the integral of x dx. So you have here t of x is equal to x squared over 2 plus c. And therefore, substituting this t of x to our solution, which is this one, then the function of xy is equal to 2xy plus y squared over 2 plus x squared over 2 plus c equals c. And further simplifying, you also have the same results of rearranging the terms, x squared plus 4xy plus y squared is equal to c, which is the same as this. Okay? So to summarize and to give you a guide on what are the procedures that you have to follow, maybe this will help you to easily remember the procedure and how we are going to solve exact differential equation. Okay, so these are the processes. Step 1, we differentiate. Step 2, we integrate. Step 3, we again differentiate. And step 4, we integrate. If we use m, let us look at this. If it is m, the first thing is we differentiate with respect to y. Then we integrate with respect to x. We differentiate with respect to y and also with respect to y. So if you are to use n, it should just be the other variable, the opposite one. So you have differentiating with respect to with respect to x, integrating with respect to y, and then differentiating and integrating with respect to x. This is the summary of the methods or the steps that you are going to follow if we are to solve exact differential equation. And these procedures are actually the same as what is stated on the two slides that I presented a while ago.